welcome to this small session on the exercises for this week, where the main focus is to have you start thinking about setting up a feed-forward part of a neural network. So if you go back to the lecture notes from this week, so one of the things we want you to go through, and this is perhaps a little bit more of interest for next week, is the use of the chain rule to set up the derivatives for the various gradients. And they enter the calculations of the backpropagation or the implementation of the backpropagation algorithm. So the gradient descent is different things than backpropagation. Backpropagation is simply you implementing the chain rule and getting the analytical expressions for the derivatives. And then you have to implement these derivatives in the gradient descent in order to train the parameters. So just think of this, the backpropagation is essentially, just stated differently, is the application of the chain rule where you start at the endpoint and you propagate backwards to the initial layer. And the backpropagation gives you all these partial derivatives, which you then need to implement in a gradient descent method. But that's the topic for next week's exercises. If you feel that, we are moving a little bit too slowly ahead, feel free to jump into that part as well. So this is, something which we will leave to you. However, if you now scroll down after these examples, which we went through during the lecture this week and also last week, where we looked at a neural network with one hidden layer and two nodes. And then we found all these expressions for the gradients. And these are the expressions which we need to update with a gradient descent algorithm. But if we now look at the things which are essential for setting up a neural network, there is a figure here which is a little bit blurred, but which now in a way contains the basic first step where you have the input nodes, and then you're setting up the weights and the biases. And it means that you have a function, the activation function, which then receives this input. And you can write this as a matrix transpose times the input plus this bias vector. Alternatively, if you reorganize the matrix, you would just have the vector A times the matrix W. This depends on how you organize the matrix elements. So that's take a look at that figure. And then if you scroll down, we have set up the final expressions. But what I wanted to remind you of are now the basic parts of the the neural network algorithm. So the feed-forward pass is the one which we want you to think of. So that means that you need to think of how you set up your inputs and outputs, define the number of hidden layers and nodes, and the exercises this week, in a way, are forcing you to think in these directions. And then you need to define the activation functions. This is something which becomes important when you're putting up the backpropagation. You need to define the optimizer. And then that's for the derivatives. You need to define a cost function. That's important when you now are feeding the output from a feed-forward pass to the cost function. You need to initialize weights and biases. And you also need to fix the number of iterations. So when you're setting up the exercises this week, it's essentially the feed-forward pass. And for the feed-forward pass, what you need to think of is the inputs and outputs. What are their dimensionalities? Then you find the number of hidden layers and hidden nodes. That defines the size of the weight matrix and the size of the bias vector. Then with the activation functions, you have another element of the architecture. Cost function and regularization terms are the quantities you use to optimize and find the optimal parameters. And then you need to initialize these weights and biases. And typically that's done by setting them to some random value. And then clearly you need to fix the number of iterations. And then next week, we have the backpropagation part. And when you have these elements, then you have the training of the parameters. And then the number of iteration tells you how many times you're going to perform a feed-forward pass and a back propagation pass. But the reason why we wanted to split this in two parts is simply because we want you to think about the dimensionality. And in the exercise text, you have the possibility to define a flexible neural network, where the only thing you define is the number of layers and the number of nodes you have in the layers. So that you don't need to go by hand and just increase the number of layers and say, if number of layers is 1, add this number of nodes. If number of layers are 2, do that. Now you can just simply set up from the beginning the number of layers and nodes. So this is the things we want you, these are the lines we want you to think along. So maybe we are a little bit too pedantic, but we often see that people struggle with setting up a neural network. Now, this week, there is also some additional material, and this additional material is about classification. And the material which you find here is essentially a reminder of what we did in week 38 and week 40 about logistic regression. So I just wanted to sneak in that element before we start working here on the exercises. So in project number 2, you also need to set up a logistic regression case or classification case. And the common function which we use is this logistic function, which then is used to classify whether you have 0 or 1. So that's one of these activation functions which we are going to use again and again and again. And logistic regression actually uses this function in order to set up a probability. So this is the sigmoid, or some people just call it the logistic function, or just the logit function. So you will find it in many different names here. And then what we did in week 38, so this is just a plot of the functions, I'm going to skip that, was simply to define a 2-parameter model where now we have 2 parameters, beta 0 and beta 1. So when you're implementing your logistic regression code, you can actually use the examples we have here. And there is a code example at the end, which we discussed in week 40 on logistic regression and how you can implement that with gradient descent. So feel free to use that code, or take your neural network and leave out the hidden layers and just have the input and the output. And that gives you essentially a logistic regression. So the probability distribution which we set up in the lectures in week 38 was this one. And now I just wanted to remind you of the logarithm of the probability distribution. So the cost function becomes this equation here. That's the one we derived, and this is actually 4 weeks ago, close to a month. And this is the one which we would typically then optimize in logistic regression. When you do that, you can either maximize, which is the first equation, or you can minimize by just taking minus log. This function is something which you will see again and again in different codes, and in the literature, it's called the cross entropy. Because it actually looks like the equation for the entropy, for those of you who have seen either the information entropy or entropy in physics courses. And then you minimize it, and when we did that, what we ended up with was to take the derivative. If we had only two parameters, beta 0 and beta 1, this is what we would end up with. So in that case, we have only 2 features, one beta 0 and one beta 1. And that's a very simple model which we have. And if you do this in a more compact way, we ended up with this expression here for the gradient. And that's the one we need to program, where this y is now the data, And these y's are either 0 or 1. And p here is what your model is producing. So with the values of beta 0 and beta 1, what you have then is simply the input to this probability here. So this will give you an output 1, and this gives you an output 0. And you can add regularization terms and make things more complicated. And the second derivative, so this is actually a convex function, which means that there is a global minimum. And you can extend this to more features, or predictors, as they're often also called. So you can have more features, beta 1, beta 2, etc. So if you look at the cancer data, you have 30 features for something like 500 patients. And these 30 features are things like the size of the tumor, the radius, the surface, etc., etc. You can include more classes, and this is something we will discuss next week when we actually implement a neural network code fully on a classification problem. So the binary case is normally given by this simple cross entropy here. Then this function can be modified if you have more cases. And we will discuss this a little bit more in detail. And if you have more cases, the function which you would use then for the probability for a given class. So this C here is a specific class K. So this could be the 10 handwritten numbers. So there's a data set which is called MNIST. So that's NIST stands for the National Institute for Standards in the US. And they collected something like 80,000 handwritten numbers between 0 and 9. And then you want to classify on this. So these are just images. And that means that you have 10 classes. And in that case, you increase this probability here, or the standard sigmoid, to the so-called softmax function. This is a standard choice when you have more classes. We are coming back to that next week in the setup of a neural network code for classification of many classes. For project 2, however, we would simply recommend that you stay with a binary case, because that's, in a way, it's a little bit simpler to keep track of. But you can make your code flexible so that you can also include this function. That function you see there, that is for the output layer. So that means that if you have a classification problem like the cancer data, you have one output, either 0 or 1, for each patient. Either it's a benign tumor or it's a malignant tumor. If you're dealing with a classification of these handwritten numbers or other cases, suppose you have 50 painters and you're making a classification of what is a Van Gogh, what is a Munch, what is a Leonardo da Vinci, Raffaello, and so on, and you make the classification of all these paintings, you could have 50 painters. And then you plug in the paintings of these 50 painters, and you train a model to recognize whether that was a Raffaello or Michelangelo or a Van Gogh or Munch or whoever. So that would be a case where you would have 50 classes. So you can clearly expand upon this, but the standard choice for this type of classification problems is either this softmax or just the simple binary case, which is given by the logistic function or the sigmoid function, as we normally would call it. Okay? So if you scroll down at the end of this additional lectures, or if you go down to the week 40, you will then find a gradient descent with logistic regression. So look at that example, because that gives you simply the way you could implement it yourself, or, as I said, you can use your neural network code. And then you can compare the results with those which scikit-learn gives you. So in this specific case, you can see now I have some initializations, I have the learning rate, the number of iterations, and then I define my sigmoid function here, which you will see again and again. This is my gradient descent, and I put in number of iterations. I have my linear model, which is just the design matrix times the beta values. So if you go back to that example which we had in the very beginning here, let me just scroll up here. I'm just plugging in the sigmoid function, which we have here, that one. And I'm calculating the derivatives, which you also see here. I'm plugging in these derivatives. That's my gradient for logistic regression. So if you scroll down here, you see now I have my gradient. I just interchanged y predicted minus y. Then I update the gradient by multiplying with the learning rate times the gradient, as before. So when the only thing you would need to plug in here, if you're using automatic differentiation, is the expression for the cost function. And then the automatic differentiation finds the explicit expression which you have here. But now I'm hard coding it. So it, hopefully a little bit more transparent. And then you see now that my linear model is given by the x, the design matrix, times this new value for the beta parameters. And my prediction is now the sigmoid, which receives the input. And then you see that if it's this I here, the y predicted, is larger than 0.5, I give 1. And then y, if it's less than 0.5, then my y predicted returns 0. So that's a very compact, this statement here is a very compact way of plugging in the y predicted. So if y predicted is less than 0.5, it returns 0, else it returns 1. So that would be my output here. So coding the logistic regression is, when you have the gradient descent, is pretty, how to say, straightforward. The only thing you need to plug in is the new cost function. That's the main difference. So I want you to see this kind of level of abstractions that if you write a more general code, what you typically would need to define for a neural network also would be the dimension of x, which reflects the number of features you have. And then with that, you also define the weights and biases, the number of hidden layers, and then you have the dimensionality of your neural network. Here it's much simpler because the logistic case is the same as a neural network with no hidden layers. It's you feeding in to a node, which now is the sigmoid function, and that produces an output. And the output is now given by the y predicted. So you could actually use your neural network code, or you could simply take this code here and implement that. Now the case here is pretty simple because I just have a so-called AND gate, and I have only, so you have two features. So bit 1 and bit 2, 0, 0, 1, 0, 0, 1, and 1, 1. So this is a 4x2 matrix. I don't know if you are familiar with an AND gate. So let me just quickly say something about that. So what you would have, if you think of a so-called AND gate, if you're not fully familiar with that, you typically have an input, which we call code X and Y. And these are either ones or zeros, and it produces an output. So you would then set, so let's call this for Z. So you can then set up a table, X, Y, Z. And you have 4 cases because you have bit 0, 0, and that produces bit 0. You have bit 0, 1, that produces 0. You have 1, 0, and that produces 0. And then you have 1, 1, and that gives you a 1. So these quantities you see here, these quantities would then define your X matrix. So you have just two features, X and Y. So your X matrix would then simply be given by 0, 0, 0, 1, 1, 0, 1, 1. And your output, and if we call that one for, so these are vectors now, Y, that would simply be given by 0, 0, 0, 1. And then we are going to have a model that can output either 0 and 1. So if you go back to that simple logistic regression code, if the sigmoid function has a value less than 0.5, it spits out 0. If it's larger than 0.5, it spits out 1. And then we can train a logistic regression function on this data set. Now, the thing is that now you have only, in this specific case, you have only 4 data. And that's a little bit too small if you want to do a training. So what you can do then is actually to make replicas of this function here, of this design matrix. So you can simply increase this by 1, and that gives you an 8 times 2 matrix. You can repeat it. You have a new data set. You get a 12 times 2 matrix. Then you get 16 times 2, and then you can just increase this one by just simply augmenting your data matrix here. So the number of inputs. But the number of inputs and the way you end up with the output is always given by the values of these bits. But you can simply just increase this one by just replicating it again and again. And it doesn't need to come in this order which we put up here. You can just change the order. And then you could train it with more and more data, and then your model would become better and better. But if you just stay with this simple case here with only 4 input values, then normally the training is not going to be very good at. And you will see that if you run that code, you will not get 0, 0, 1, but you may get 1, 1, 0, 1. If you increase this design matrix, it's going to give you a better and better fit. So that's a very classic case, which has also been used in the training of neural networks. As an example of where these logistic models actually fail, because there is a famous gate, which is called the XOR gate. And the XOR gate is something you cannot predict correctly with a linear model like the one we are setting up now. So we have a linear model in terms of the parameters beta. Because the XOR gate is a little bit different. So if you think of what you see here, you can understand why a linear model can make a prediction here. So if you plot the results in terms of X and Y, so if this is X, so you have 0 and 1, and this is Y, you have 0 and 1. Then we know that when it's 0 and 0, then we get 0 here. So let's mark that one with a closed circle. We get 0 here. We get 0 here, but then we have a 1 here. So a linear, you see now that if you are able to find a line which separates these classes, then you can say that if my value is below, then I predict 0. If it's above this line, then I predict 1. So you see why intuitively now, why you can predict or you can find a line which separates the 2 outputs. And then you can define a model which gives you the parameters of this line. And then you simply find that your prediction here would be y is equal to some alpha times some beta times some parameters, or let's now call this x. It's actually wrong to call it x here, but we could call it a delta gamma times y. It's a linear model, and then you can actually make a fit here. No, not y here, but this is a function f of the 2 parameters x and y. If you can find such a line, then you can say that if it's smaller than a certain value, we predict 0. If it's larger, it predicts 1. And there is a classic gate which is called the XOR gate, where we now have a different case. So when we have 0, 0, we predict 0. If we have 0, 1, we predict 1. If we have 1, 0, we predict 1. And if we have 1, 1, we predict 0. And this is a little bit more difficult because if you make a plot of that one, you see immediately that fitting a straight line will not work properly because we will now have 0, 1 here. So we get a 0 here and a 0 here. But then we have a, so not that one. But then we have a 1 here, and then we have a 1 here. And now you see that's not easy to make a straight line which separates properly these two cases. So the XOR gate is a case where we typically fail with a linear model. So a simple perceptron has been used as one of the test cases where you actually fail in predicting the outcome correctly here. Now, there's one thing I wanted to go back to a little bit. And this becomes important when we now are looking at the classification problem. So let's go back to the cancer data. And this is just a Jupyter notebook where we run through and make a fit with the breast cancer data. So this is taken from the lecture notes in week 38. And here we load from scikit-learn. It's actually a library which we have access to. This is also useful when you want to compare your neural network code with some other codes like scikit-learn, those which scikit-learn offers you. And you see now that it has logistic regression as a linear model. And we do the standard train test split. I'm not scaling here. I just keep this as simple as possible. And I run the logistic regression where we now have a so-called quasi-Newton method where we try to estimate the Hessian matrix iteratively. So for the case which we have here, we could actually calculate the Hessian matrix. This method stands for, I think B is for Broyden, F is for Farberg, and I don't remember the acronym for the other authors. There's actually 5 authors. And it's an option which you have. So this is a solver. So this is a quasi-Newton method where you actually try to estimate the Hessian matrix in the first iterations, and then you use that iteratively to update the Hessian matrix. So it's a better way than just doing gradient descent. You can do gradient descent also, but scikit-learn contains many different solvers here. So in this specific case, if I run it, I'm going to get a total, when I split the data like this, so you see you have something like 500 patients. This data set has something like 30 features. And the logistic regression, the accuracy is roughly 94%. This is the accuracy for both true, false, positive, false, etc., which we are coming back to. And I will show you different ways by which you can analyze the data. There's something which we discussed early in the semester, which is called the correlation matrix. And that is a matrix which takes values between -1 and 1. And you can actually make the correlation matrix and plot it. And you can also plot the different features. We mentioned this roughly during the lecture in week 38 and week 39, long time ago. But this is a nice way to actually plot some of the features. So you will see now, if you scroll down here, you will see many different features which are used by the pathologists to classify the tumor. And you see here, like a mean radius is something which is often used as an indicator of whether this is a bad one or a good one. And then you have other features where it can be more difficult to discern the two cases. So when you actually imaging of this type, of tumors is something which is widely done by machine learning. Because to train a pathologist is something you spend a life on. Because you need a lot of experience to recognize the tumors. So one of the big applications of machine learning and imaging in particular is actually to analyze scans of tumors. That's a huge field in medicine, and it has given people like pathologists and people in the oncology department, it has given them an invaluable tool. Because it takes often days for one person to go through the tumors and look at the scans. Whereas now, if you train properly a model, you can flag the dubious cases. So this is an extremely powerful tool, actually. And if you're thinking of master thesis and so on, that's a very important field of applications. Now, the correlation matrix varies from -1 to 1 in value. And you will see now that typically the mean radius, and if you compare that with something like the mean area, which is this one, they have a strong degree of correlation, obviously. So some features are strongly correlated and some are less. And these are also things which you can extract from the different features. So I think there are something like 30 features here. More or less. I don't know what they all mean, obviously, because I have never dealt with oncology as a field, so I wouldn't be able to tell what they actually mean. But this would be a way by which you can try to find information about correlation data. Now, there is another way to classify, and scikit-learn provides us with a tool which is extremely valuable. And these tools are included in a package which is called, so if we scroll down a little bit, you will find now the possibility to calculate. One first thing is the accuracy, where you simply count the number of cases which are correctly classified and wrongly classified. But there is something which is called the confusion matrix. And I just wanted to say a little bit about that. That's an extremely useful way to classify things, because you can classify this in terms of true positive, which means that you correctly indicate a positive result. You can have a true negative, which gives a correct negative prediction. So you have to decide what is negative and positive. I would clearly say that positive would be a benign tumor and negative would be a malignant tumor. And then you have to classify these correctly. And then clearly you can have a false positive, which is often called a type 1 error, where you simply have a wrong indication that a specific attribute is present. And then, so it's pretty obvious, false positive and false negative. And this is something you can then plot in terms of the confusion matrix. There is another property which is also called the ROC curve, and there's also something called the cumulative gain, which are often used. But if we look at if we make a run now, you will then see that our logistic regression overall has a 94% hit rate, which means that we classify all the events, whether they're positive or negative, with a correctness of 94%. But we may be interested in understanding how many of the true positive are correctly classified and how many of the true negative ones are correctly classified. You will also see that you need more iterations here. So this is some typical flag which you will get when you run it. And this is the confusion matrix. So let me see if I can reduce the dimensionality here a little bit. Nope. It's my window here, which is small. So this will be true positive. And you see now for the true positive, I classify 96% correctly. And the true negative gives now a 93% accuracy. And then you have a true or false negative, and then a false positive here. So this is a way to break down the information and to display it rather quickly. I often like to, when I do a classification problem, I like to not only display the overall accuracy. So this number here, 94%, is you counting the number of correct predictions and divide by the number of prediction of outputs which you have. So if you have a 1 here, you have 100% correct training. Yeah, yeah. Yeah, yeah. 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 Mm. Yeah. Yeah. Exactly. Yeah. Yeah. So I actually like this very much because it gives you, just in one graph, it gives you the immediate understanding of how your model is doing. And I would say, as Ida says, that the 7% false negative here is not good. So it's 7% of the cases. So this training which we've done is perhaps not the best one. Actually, 94% accuracy is, depending on how you see it, I wouldn't say in classifications of tumors, it's not very good. So you would rather like to be close to 100% in both cases. Yeah. Actually, this is a, yeah. Say again. Exactly. So actually, this is a huge field in applications. Oh yeah, that is Siri who's listening to me. Sometimes it just pops in and says, "I didn't get that." Okay, let me just take it out. Yeah. Okay, so this is a very nice way of doing it. And then there is something which is called ROC curves, which then takes ratios of about, so there's something which is called the TPR, which is a sensitivity hit rate on the true positive rate. I'm not going to go through that here now, because this is another way of representing the way you classify properly. And if you're interested, we can discuss this on a more one-to-one basis. But I have a set in the lecture notes where I actually discuss what these different quantities are, because you can make combinations of true, false, true, negative, etc., and classify things in many, or present things in many different ways. But normally for a classification problem, I myself actually, I prefer the confusion matrix because that gives a lot of information immediately. Now, some of the other curves are very useful if you want to see how well the model is doing in training. Yeah.
If you use that for example, the numbers.
Yeah.
You need one for each.
Yeah.
Number.
Yeah. Exactly. Yeah. But you see, when you if you want to use that in project 1, now in project 2 here, we simply recommend to use these functions which you have in scikit-learn. And this is the plot confusion matrix. So you have the metrics package, which you would simply then include here. So you have the, so where did I include it actually? Yeah, from the scikit-learn pre-processing. And then we have import scikit-plot as skplt. And that contains these metrics packages, both the ROC curve and also the cumulative gain, which are different ways of classifying or presenting the results of a classification problem. So I'm going to stop here this was a kind of me sneaking in a kind of additional lecture, but it's also to remind you of where you find the information about the logistic regression and the type of cost function which you have from logistic regression, which then enters project number 2. But for project number 2, the important thing now is actually to start thinking about the setup of a neural network.